On November 18th of this year, at 2 hours, 16 minutes, and 7 seconds past midnight, Pacific Standard Time, a machine launched before the internet existed, will reach a distance of exactly 160,094,799,096 miles from Earth. That number is not a projection. It is not an estimate. NASA published it to the second. At that distance, a signal moving at the speed of light, the fastest anything in the universe can travel, will take exactly 24 hours to reach it. 1 full day just for a message to arrive, another full day for any response to come back, 2 days of silence between every question and every answer. No human-made object has ever been that far from home, not once in the entire history of civilization. And this one will cross that threshold while it is still alive, still transmitting, still sending back data about a region of the universe that every scientific model built to describe it got fundamentally wrong. It runs on roughly 4 watts of power. The small light inside your refrigerator uses more electricity than that. It was built using technology that predates personal computers, and right now, this summer, NASA's engineering team at JPL is in the middle of executing the riskiest procedure in the mission's 49-year history, a simultaneous reconfiguration of every remaining power system on the spacecraft that the team nicknamed the Big Bang, with the outcome determining whether an instrument shut down 3 months ago gets switched back on, or whether the most complete data stream from interstellar space begins its final decline towards silence. Stay with me because this is the story of Voyager 1, and what it found beyond the edge of our solar system is not what the textbooks say. I am narrator name, and this is channel name. Subscribe now if you want more stories like this because we are covering the Big Bang results, the November milestone, and every piece of what happens next. And let me go back to the beginning. September 5th, 1977, a rocket lifts off from Kennedy Space Center carrying a spacecraft called Voyager 1. The mission plan is simple. Swing past Jupiter, swing past Saturn, take photographs, collect measurements, and then drift away into space and go quiet. The expected lifespan is 4 years, maybe 5. NASA plans to wrap it up around 1981 or 1982. A nice set of postcards from the outer solar system, and then silence. What actually happened is one of the most extraordinary sequences of events in the history of science, and most people have no idea how extraordinary it actually is. Voyager 1 did not go quiet. It passed Jupiter in March of 1979 and sent back the first close-up images of that planet's atmosphere that human eyes had ever seen. It passed Saturn in November of 1980 and kept going, using the gravitational pull of each planet as a slingshot to add more speed, more distance, more territory covered. By the end of the 1980s, it had already traveled farther from Earth than any object humans had ever sent into space. And it was still transmitting, still sending its thin signal across the growing void, still collecting data, still functioning on hardware that modern engineers look at and shake their heads at in disbelief. Then, in August of 2012, 35 years after it launched, something happened that made the entire story suddenly much bigger. Voyager 1 crossed the Heliopause. That word matters. The Heliopause is the single most important physical boundary in our cosmic neighborhood. The sun does not just provide heat and light, it constantly releases a stream of charged particles called the solar wind, blowing outward in every direction, pushing against the surrounding space and inflating a giant protective bubble around our entire solar system. That bubble, the heliosphere, contains every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed. The outer edge of that bubble, the point where the solar wind finally runs out of energy and gets stopped by the pressure of interstellar space pressing inward from the other side, that is the heliopause. It is the actual physical boundary of our solar system. Everything inside it is ours. Everything outside it is something else entirely. In August 2012, Voyager 1 crossed that boundary and came out the other side. It became the first object in human history to leave the solar system. Not a metaphor, not a technicality, the first physical thing our civilization has ever sent into the actual space between stars. And then it kept transmitting. Think about what that means. We have right now a live instrument sitting inside interstellar space, not orbiting a planet, not floating in the outer solar system, not near the heliopause, actually inside the dark, cold, ancient space that lies between star systems, a space that no scientist, no telescope, no model built from the ground has ever been able to directly observe from the inside. And what it has been telling us about that space is not what anyone expected. For decades before Voyager 1 got there, physicists had built detailed mathematical models describing what interstellar space should look like. Not guesses, serious, peer-reviewed, rigorously tested models built by some of the smartest people alive. Those models all told roughly the same story. Interstellar space should be relatively quiet, relatively smooth, a thin, cold, sparse environment where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 walked into that waiting room and found it was a storm. Starting in 2017, the plasma wave instrument on board began detecting something nobody expected and nobody could immediately explain. A persistent narrow band emission, a faint but constant hum in the fabric of interstellar plasma that, according to every model built to describe this environment, simply should not be there in the way it was. Not a one-time burst, not a spike that could be dismissed as a glitch. A continuous signal, year after year, stretching across a distance of roughly 10 astronomical units over 900 million miles of interstellar space. The distance from Earth to the Sun is 93 million miles. This emission was detected across a stretch of space more than 10 times longer than that. Stella Koch-Acker, a Cornell doctoral student in astronomy and lead author of the study published in Nature Astronomy in May 2021, described what she found in terms that were careful but unmistakable. We are detecting the faint, persistent hum of interstellar gas. Her co-author James Cordes, the George Feldstein Professor of Astronomy at Cornell, compared it to gentle rain. Researchers concluded that interstellar space is not the quiet, uniform void that models described. It is turbulent. It has structure at every scale, from distances measurable in meters to distances measured in millions of miles. It has, in a physical sense, weather. And we were completely blind to all of it because we had never had a single instrument inside it before. Now stop and sit with that for a second. Every model built to describe the universe beyond our solar system was constructed from the outside looking in, from a planet, using telescopes and mathematics and theory. The first instrument we have ever actually put inside that space is telling us those models were missing something fundamental. The universe beyond our solar system is more complex, more dynamic, more structured than we knew. But here's the part where this stops being abstract and starts being personal. Because those discoveries do not stay out there. They reach back here. The heliosphere is not just a boundary line on a scientific diagram. It is a shield. It deflects the most dangerous forms of cosmic radiation, the high-energy particles streaming in from distant exploded stars, from reaching the inner solar system at full strength. If the interstellar environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than our models accounted for, the implications for how well and how consistently that shield protects life on Earth over geological timescales are significant. Voyager 2's crossing data, published in 5 simultaneous Nature Astronomy papers in November 2019, established that the interstellar magnetic pressure on the heliosphere is roughly 10 times greater than pre-crossing models assumed. That stronger external pressure means the heliosphere is being compressed more than anyone calculated. We do not yet know exactly what that means for the long-term stability of the shield itself. But the fact that we now need to ask the question at all is itself a shift in how we understand our own vulnerability as a species. If you are the kind of person who stays for the real science, drop a like right now because it genuinely helps this kind of content reach the people who want to hear it. Now, I need to tell you what happened in late 2023 because this is the part of the story that turns it from a tale of discovery into something closer to a rescue. For 5 months, Voyager 1 continued to transmit a signal back to Earth, but what it was transmitting was gibberish. Corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything this spacecraft had ever sent, could not decode. The instrument was still alive. The signal was still coming. But whatever it was trying to say had become unreadable. The cause, when they finally identified it, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation. One small piece of 1970s hardware, one chip measuring a fraction of an inch, had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had gone off, no warning had been sent. The chip had just quietly failed after 46 years of non-stop operation in the harshest environment a human-made object has ever been placed in. The only tools available to fix it were radio signals traveling at the speed of light, and even those signals took 22 hours one way to reach the spacecraft, 22 hours just for the message to arrive, another 22 hours for any response to come back. Every single diagnostic step required a minimum of 44 hours to complete a single round of communication. Think about what that process actually looked like from inside the control room. You look at a piece of data, you form a theory about what might be wrong, you write instructions to test that theory, you transmit them. You wait 22 hours, you receive whatever the spacecraft sends back, you analyze the response, you discover something slightly different from what you expected, you form a new theory, you transmit again, you wait 22 hours again, you continue this process step by patient step for months, and every moment carries the knowledge that a single wrong instruction sent once across 15 billion miles of void could permanently end the mission with no recovery possible. The team at JPL worked through this for months, carefully, methodically, under a kind of pressure that most engineering situations never produce, and they succeeded. They figured out that the corrupted code could not be repaired, but it could be relocated. The affected portion of software was split into smaller sections and stored in different places in the spacecraft's available memory, each section individually checked and rewritten to function correctly from its new location, then carefully reconnected to work as a whole. It was brain surgery performed remotely through a 44-hour time delay on a machine nearly 50 years old sitting 15 billion miles away. In mid-2024, Voyager 1 came back online and began transmitting clean, readable, complete scientific data again. And what it immediately resumed sending home was more evidence of those persistent, unexplained plasma oscillations in interstellar space. Now let me bring you to what is happening right now, because the story is entering what may be its final chapter, and the timeline is tighter than most people realize. On April 17, 2026, NASA sent commands to shut down Voyager 1's low-energy charged particle experiment, an instrument that had been collecting data almost without interruption for 49 years. Not because it stopped working. It was still working fine. It was shut off because there was no longer enough power to keep it running. Voyager mission manager Kareem Badruddin said it directly. While shutting down a science instrument is not anybody's preference, it is the best option available. Voyager 1 now has 2 functioning science instruments remaining, the magnetometer and the plasma wave subsystem. 2 instruments out of the 10 it launched with. Both spacecraft lose approximately 4 watts of power per year from the steady decay of plutonium-238 in their radioisotope thermoelectric generators. At launch, those generators produced around 470 watts. Today, the output is a fraction of that, and the margins are razor thin. Power has grown so scarce that the team has had to shut off heaters for components, risking fuel lines freezing in the cold of interstellar space. Every decision to keep one system alive is a decision to let another one die. But they have not given up on getting more time. The Big Bang procedure is underway right now. Testing began on Voyager 2 in May and June of this year, since Voyager 2 has slightly more power available and is closer to Earth, making it the safer test subject. The procedure involves swapping out thruster fuel line heaters for 3 lower power alternative devices all at once in a single coordinated operation to minimize the time spent in dangerous intermediate power states that could trigger automated fault protection systems. If the Voyager 2 tests succeed, the same procedure will be attempted on Voyager 1 no earlier than July. And here is the detail that makes it matter. NASA deliberately left a small half-watt motor running on the LECP instrument after shutting it down, specifically to preserve the possibility of restarting it. If the Big Bang works, there is a real chance that instrument could be switched back on. Matt Hill, principal investigator for the instrument at the Johns Hopkins Applied Physics Laboratory, said it in an email. We hold out hope that the Voyager engineers' latest plan will be able to power up LECP on Voyager 1 again to let us continue to learn whatever surprises await Voyager in these distant regions. And then comes November. On November 18th, 2026, at 2:16:07 in the morning Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth, 16,094,799,096 miles. NASA published the number to the mile. At that distance, if you send a command on a Monday morning, you will not know if it arrived until Tuesday morning, and you will not receive the spacecraft's response until Wednesday morning. 2 full days of silence for a single exchange of information. No human-made object has ever been that far, and on that date, Voyager 1 will cross that threshold while it is still alive, still transmitting, still sending back data from interstellar space, and then it will keep going. Every hour it travels roughly another 38,000 miles deeper into the dark. The communication delay will keep growing, the power supply will keep shrinking, and at some point in the early 2030s, the last signal will come. Here is what I want you to take away from all of this. Right now, in 2026, the only live scientific instruments humanity has ever placed in interstellar space are running on technology from an era before personal computers. They are powered by less electricity than the light above your kitchen stove, and they are sending back information that is changing how we understand the universe and our place inside it. The space between stars is not empty, it is not quiet, it has weather, it has texture, it has structures built from charged particles and magnetic fields that stretch for millions of miles and interact with the outer boundary of our solar system in ways that no model built from Earth could detect or predict. And the shield that boundary provides, the heliosphere that makes life on our planet possible, is being pressed harder from the outside than any calculation accounted for. We built things that are much larger. We built things that are much more powerful. We built things that cost far more money and involve far more complex technology. None of those things have told us what Voyager 1 is telling us right now, because none of them had the one thing Voyager 1 had. None of them had the audacity to keep going long enough to actually get there. And bolted to the frame of this dying machine is something that will outlast all of it, the Voyager Golden Record, a gold-coated copper disc carrying greetings spoken in 55 human languages. The sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter, 90 minutes of music chosen from cultures across the entire history of human civilization, and a map made from the positions of pulsars designed to show whoever finds it exactly where in the galaxy our planet sits. It will still be traveling when the sun has become a red giant and swallowed the orbit of the Earth. It will still be traveling after every human city and every human archive and every piece of stone we ever carved our names into has been erased by geology and time. It is the most permanent thing our civilization has ever made, and it is riding on a spacecraft that currently runs on less power than the light above your bathroom sink. The signal is still coming, stretched across 15.8 billion miles, delayed by nearly 23 hours of travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model built from Earth had ever correctly described. One machine, 4 watts, one chance to listen. The question is whether anyone is paying attention. If this kind of story is what you come here for, subscribe right now and turn on notifications. The Big Bang results are coming. The November 18th 1 Light Day milestone is coming. The 50th anniversary of the launch is September 2027. I am covering every piece of it. Drop a comment with what surprised you most and share this with someone who needs to hear it, because this story deserves far more than the silence it is getting. Thanks for watching, and I will see you in the next one.